Now we'll talk about the concept of a magnetic field. So having these magnetic poles, we can imagine that a magnetic pole creates a magnetic field around it. And following the ideas of action at a distance through the field, we can basically interpret the interaction between two magnetic poles to be mediated through the magnetic field that is created by a pole with which the second pole will be interacting. So in this theory, basically we are saying that a magnetic pole creates a magnetic field around it, and when we have a field in a volume, so the second point here is that having a non-zero field, magnetic field in a volume basically implies an energy gradient in that volume. So we have a change of energy with distance from a reference point in this volume. So there is an energy gradient in that volume. And if you have an energy gradient, that means when we bring another pole next to the first pole that creates the magnetic field, the incoming pole will feel a force. So an energy gradient implies a force acting on another magnetic pole when brought into this volume, so when it is brought in. So in the CGS picture, so if I go back to the force that is applying, that is appearing between two magnetic poles with pole strengths P1 and P2, this force was P1 P2 over R squared. Basically I'm just going to put P1 divided by R squared in parentheses and multiply it with P2, and with this interpretation P1 divided by R squared is what I call the magnetic field. So the force is magnetic field H times P2, so that the magnetic field created by the pole strength P1 is P1 divided by R squared, where in the CGS system H is measured in oersteds and the force is equal to P2 times H. Now if I look at the SI point of view, in the SI point of view, the force between two poles was given by mu0 divided by 4 pi, so I will have the mu0 separated here, P1 divided by 4 pi R square I will put into a parenthesis, multiplied by P2. So here we're going to call P1 divided by 4 pi R square as the magnetic field created by P1. So H is now P1 divided by 4 pi R squared instead of P1 divided by R squared, so that H will be measured in ampere per meter ampere per meter, and the force between the two will be given by mu 0 P2 times H. So the conversion between these two we can note here, and I will have a more detailed discussion on this conversion. 1 Ørsted is 1000 divided by 4 pi ampere per meter. So let's move it here. So that basically corresponds to 79, roughly 79.6 ampere per meter. So that's the conversion factor. So let's recall that the pole strength had the unit pole strength. It doesn't have a name in CGS. In SI, the pole strength is measured in ampere meters, and the magnetic field is in Ørsted with the force given by pH, and the magnetic field is in ampere per meter with the force given by mu 0 pH in SI, and the conversion between ampere per meter and Ørsted is 1000 over 4 pi ampere per meter is 1 Ørsted. So if you remember, if we had this unit strength in the CGS system, so we can say that in the CGS point of view, a field of unit strength is one, so that's going to be 1 Ørsted now, is one which exerts a force of 1 dyne on a unit pole. So we should also recall that there's a conversion between Newton and dyne. So if we go back, we can see that 1 Newton is 10 to 5 dynes. Now I have one remark about this magnetic field. There is another name for it. H is also called the magnetizing force. So if you remember our discussion in the first video, we said that the effect of the magnetic field on its surrounding, one of the effects is to magnetize. So when you have a demagnetized magnet that is brought into H, it will be magnetized. So that's what it means. When a demagnetized, we will talk about demagnetization in more detail. A demagnetized magnet is brought into H because the poles of the magnet will feel this force, so they will separate into north and south poles. The attraction between north and south and repulsion between similar poles will cause it to be magnetized. So it will be magnetized. So magnetic field is also known as magnetizing force. So we can note some orders of magnitude for magnetic fields. These are some values we should be aware of. So let's give some numbers for orders of magnitudes. We can see, well, one of the things we talked about is Earth's magnetic field. Earth's magnetic field, if you try to measure it, it is of the order of 0.5 Ørsted at the surface of the Earth. If you measure the magnetic field of a typical bar magnet, it's of the order of 5 kilo Ørsted, which is 0.5, corresponding to 0.5 Tesla. We will talk about that later. If you measure the magnetic field that you can produce easily in an electromagnet, that is of the order of 20 kilo Ørsted. If you use a superconducting magnet, you can easily achieve up to 100 kilo Ørsted. If you look at human brain, the magnetic field created by nerve impulses, because we have charged particles moving in our brain, according to Ørsted, they will create a magnetic field. It's in the nano Ørsted range. It's very, very small. And on the other hand, if you look at the magnetic field at the surface of a neutron star, we have values of the order 10 to 11 Ørsted, so quite high magnetic fields. All right, so Michael Faraday had an idea of representing magnetic fields with lines of force. So Michael Faraday, 1791, 1867, great physicist, introduced the idea of representing a magnetic field by using lines of force. Okay, so how do we represent these? You can see these lines of force will always radiate out from the North Pole and they will approach the South Pole. So it's always pointing from the North Pole to the South Pole. They originate at the North Pole and end at the South Pole. So that is the convention. And what is the connection between the field strength and with this picture of lines of force? The field strength that we are measuring in Ørsted in the CGS system, or ampere per meter in the SI system, the field strength H is defined as the number of lines of force passing through unit area perpendicular to the field. So with this definition, that's the definition of a field strength in terms of lines of force, we have 1 Ørsted, the unit field strength in the CGS system, is equal to 1 line of force that is passing through an area of 1 centimeter square perpendicular to it. This is also referred to as 1 Maxwell per centimeter square, or we can show it as 1 mx per centimeter square. So if you want to have a conversion between Maxwell, the CGS, and SI, So let's give it quick conversion here. The conversion between Weber and Maxwell. Weber is the SI unit, so we have SI Weber, and CGS Maxwell. So we can basically have 1 Weber is equal to 10 to the power 8 Maxwell. So that's the conversion factor between Maxwell and Weber. So they're just measuring the lines of force. It's a measure of flux, basically. So this is a measure of magnetic flux, the number of lines passing through a unit area perpendicular to the magnetic field. All right, so if you consider a unit sphere, I put a pole with a pole strength equal to 1 unit pole strength right in the middle. So we can see that the surface area would be, if you have a 1 centimeter radius, 4 pi centimeter square. The magnetic field at the surface would be 1 Ørsted. It is P divided by R square. So P is 1, R is 1. In CGS units, it's going to be 1 Ørsted. And if I ask you what is the total number of lines of force that you have to draw in order to represent this with the Faraday's picture, so total number of lines of force that you would have to draw around this unit pole strength would be equal to, because you have 1 Ørsted, 1 line of force per centimeter square, total area 4 pi centimeter square, it would be 4 pi lines of force you would have to throw. On the other hand, if you have a pole strength of P, we can say that 4 pi times P lines of force radiate out from a pole strength P. So that's the number of lines of force you would have to draw in order to represent the magnetic field that is coming out of a pole with pole strength P. So we will talk about magnetic flux in more detail in the next video. So let's just summarize what we have discussed here. Well, in this action at a distance picture in physics, we're basically assuming that the force that appears between 2 objects, which are 2 magnetic poles in this scenario, is mediated through a field that is generated by one of the objects, so one of the poles. So a magnetic pole creates a magnetic field around it. And if you have a field in a volume, that means you have an energy gradient. You know that force is minus the energy gradient. So you have a force that will appear on a magnetic pole when it is brought in. And in the CGS picture, a unit pole will produce a magnetic field of 1 Ørsted at a distance of 1 centimeter. And if you bring another unit pole at this distance to 1 centimeter distance, you would have a force of 1 dyne appearing on that pole. And the force that would appear on the pole that you're bringing in, P2, would be equal to P2 times H, the magnetic field created by the first pole. In the SI picture, we have mu0 over 4 pi P1 P2 over R square is the force. We define the magnetic field as P1 divided by 4 pi R square, where the magnetic field is in now ampere per meter, and the force that appears between the two poles will be mu 0 P2 times H, the magnetic field created by P1, which is P1 divided by 4 pi r squared. The conversion between these two is 1 Ørsted is 1000 over 4 pi ampere per meter, or 79.6 ampere per meter. We call this magnetic field also the magnetizing force, because when you bring another material nearby, you will cause a separation of its poles, and therefore you will be magnetizing it, so it's called magnetizing force. Typical values of magnetic fields in CGS units: Earth's magnetic field is less than or comparable to 0.5 Ørsted at the surface, bar magnet 5 kΩ, electromagnet 20 kΩ, superconducting magnets can produce easily 100 kΩ. Human brain nerve impulses create a nano-Ørsted, but the surface of a neutron star, you have an order of magnitude of 10 to 11 Ørsteds. Michael Faraday had this genius idea of representing the magnetic field using lines of force, and with the lines of force picture, the field strength H is defined as the number of lines of force passing through unit area perpendicular to the field. So the unit field strength 1 Ørsted is 1 line of force per centimeter square, which is 1 Maxwell per centimeter square. In the SI picture, we use, instead of Maxwell, Webers, and 1 Weber is 10 to 8 Maxwell. So that is referring to magnetic flux, we will talk about in more detail. So if you have a unit sphere, you put a unit pole strength in the middle, and you look at the surface, which is at a distance 1 centimeter from your pole. You have a surface area of 4 pi centimeters square. The magnetic field created by this unit pole strength is 1 Ørsted at the surface. Therefore, total number of lines of force is 4 pi. So it is 4 pi centimeters squared times 1 Ørsted, 1 line of force per centimeter square. Centimeters squares will cancel. You will get 4 pi lines of force. If instead you put a pole strength P, you would have 4 pi P lines of force radiating out from this pole.